Okay, thank you everybody for coming. This is the last seminar in this calendar year, and we're happy to have Stefano Ermon today talking about models for human decision making. As you know, part of the center, we are looking at solving problems related to autonomous driving, robotics, and with a focus on humans as the main users of this AI technology. And today we'll hear about some exciting research that really tackles on the issue of how we can model how people make decisions. All right, so with that, Stefano, thank you.
Yes. Yeah. Uh, so today I'll tell you about some of the work we've been doing with two students here, Jonathan Paul, J.H. Gupta, and Yun Lee. There were two papers, one published by SCML and one that we presented at MDPs last week. And let me start with some background. As we know, we're building AI systems that are more and more entering our everyday lives. And as a result, we're seeing more and more interactions between AI systems, computer systems, and humans. And as a result, it's becoming more and more important to come up with good ways to come up with good models of human decision making. We need these models to be able to make predictions about the kind of decisions humans are going to do in the environment, and also because we need to understand how human makes decisions if we want to be able to imitate and build better AI systems. So these problems come up all the time. If you think about autonomous driving, we need to figure out how pedestrians will behave. If we want to drive safely, we need to figure out how other drivers are behaving on the road, and we need to react accordingly. We need these kind of models to anticipate actions that maybe a driver in the car in our autonomous vehicle will take, or other drivers in the environment will take. And the other big application of this kind of models is that we can use them to actually imitate expert behavior. So if we have a model of how a human makes decisions to solve a complex task, we can actually use this model to come up with an automatic way, an artificial way to solve the task. We can do essentially imitation. And that's what I'm going to be focusing on today. So let's delve in. So the basic framework that we're going to use to capture rationality and decisions over time is the framework of Markov decision processes. How many of you have seen MDPs? Pretty much everybody, good. So that's great. Brief reminder. We have MDP is defined by several parts. We have states that are shown, I think, in green here. We have three of them, S0, S1, and S2. We have actions that our agent can take in this environment. And in this case, we have two of them, A0 and A1. There is a reward function that maps states to real numbers, rewards. In this case, I'm representing them with these blue arrows. We get a reward of 0 when we are in state S2, 1 when we are in state S1, and 5 when we are in state S0. And there are transition probabilities. Whenever we are in state S and we take action A, there is some probability of transitioning in a new state. So for example, if we are in state S0, we take action A0, then there is probability 1/2 of moving to state S2, and with probability 1/2 we stay in state S0. And so this is a very general modeling framework. You can capture a lot of different problems in this way. And the basic object that we're going to need to describe how a human or an agent makes decisions in this environment is a policy. Policy is describing how we make actions. And mathematically is a mapping. In this case, it's going to be a mapping from states to actions. And we're going to assume that the agents that we're going to be considering are, so for example, it could be something like this. When we are in state S0, we take action A1. When we are in state S1, we take action A0. When we are in state S2, we take action A0. And we're going to assume that the agents we are dealing with are rational, in the sense that they maximize some total potentially expected, and maybe can also be discounted reward. So there are multiple ways in which you can interact with this environment. There are multiple policies that you can choose, multiple ways in which you can take actions, and one, in some sense, optimal way to interact with this environment is that of trying to maximize the total expected reward. And there is an expectation because there is some stochasticity due to the transition probabilities, and maybe also due to the policy, which could be stochastic. And there might be a discount factor that is basically capturing the fact that we might have a preference for rewards today rather than tomorrow. Questions on the basic setup? All right.
Something logistics. If you can try to speak closer to the microphone.
Okay.
When you go that way, it seems like they lose the audio.
All right. So the basic problem given an MDP is that of trying to compute such an optimal policy. In the past few years, there has been a lot of progress in solving fairly complicated reinforcement learning tasks. For example, solving problems like Atari games, even learning how to compete with some of the best Go players in the world with a computer, and complicated robotic manipulation tasks. And for example, we might have the game of Pong that we have here. We can think of this as being some kind of environment, and we want to build an agent that learns how to play Pong. So the agent will be in different states, which are given, might be given by the raw pixels that represent the screen. And there are actions that the agent can take. You can move the paddle up or down. And the basic problem in reinforcement learning is to figure out how to come up with a good policy to solve this task. How to figure out how to compute a mapping that maps these states. In this case, could be just a simple representation. Could be one frame or 2 frames or a difference of 2 frames, and it maps them to actions. And this problem is complicated because the observations are high dimensional. It could be just some raw pixel values. And so learning a mapping from raw pixel values to actions can be very complicated, especially if it corresponds to a good policy. It's describing this kind of interesting high reward behaviors is complicated, but it has been made possible using these very powerful function approximators like deep neural networks, and somewhat surprisingly, it's possible to train them, essentially doing gradient descent, and it's possible to learn how to solve these pretty complicated tasks. But one of the issues of this kind of setup, of the reinforcement learning setup, is that you need a reward signal. You need some way of defining whether you're doing well or bad in this environment. In this case, for example, whether you win or lose the game. That's essentially the signal that you're using during training to figure out whether your policy is good or bad, and sort of get a signal for figuring out how to change your policy and get an improvement. And this is a natural assumption, the fact that you have a reward in many settings is definitely very natural. If you think about Atari games or Go, where there is a clearly specified reward function. But there are many other scenarios where defining a reward function is hard. For example, if you think about how to drive a car, it's not so obvious how you would define a reward function that corresponds to a desired driving behavior. You might want the car to move forward, but you don't want it to move too fast. You don't want to go off the road. You don't want to hit other cars. You don't want to hit pedestrians. But it can be very complicated to specify the right reward function. So in some settings, a natural setup is to provide supervision in a different way. And we can consider a different setting where we have an imitation problem. but instead of having access to a reward signal, we have access to behavior, expert behavior, that is generated by an expert. So for example, we might get to see in this toy highway driving simulator, you might get to see how this blue car is driving around, and you want to sort of imitate this behavior. You want to figure out whether you can come up with a policy that drives like this. And maybe you can have different types of behaviors. You can have a more aggressive drivers. You can have a more defensive driver, and you want to be able to figure out how to imitate the behavior purely from demonstrations without access to a reward signal. So is the problem clear? All right. So formally, the problem is like this. We are given a set of trajectories, so states and the corresponding action that is taken by the expert. Here phi E is a policy that is the expert policy. And the goal is to learn this policy function. So remember, a policy is a mapping from states to actions, potentially stochastic. Yeah.
So in the Markov decision process interpretation, is your state just your current state, or is it your state history, like your whole trajectory history?
Oh, we're looking at Markovian.
So just your current state?
Just the current state, yes.
Can you also repeat the question?
The question is, if the policy is history dependent, or is only Markovian is only looking at the last state. So you might think that this is this sort of like a standard supervised machine learning problem. After all, we are being provided with a bunch of examples of states and corresponding actions, and so we might just try to throw this at your favorite deep learning or whatever machine learning technique. But it turns out that this doesn't really work. So we can try, or sometimes at least it doesn't work. We could try, we can think about, for example, generating or obtaining from the expert a data set of states and corresponding actions, and we can try to learn a policy either by doing standard supervised learning or regression if the actions are, say, continuous. And you can definitely do it, but the problem is that no matter how good your learning algorithm is, it's going to make some mistakes. And what will happen then is that when you're going to try out your policy into the environment, this learned policy into the environment, what will happen is that sooner or later, the policy will make a mistake because it's not perfect. You haven't been able to learn perfectly this mapping from states to action that corresponds to the expert. And what will happen is that these small errors will cascade over time, especially because there is likely going to be some kind of covariance shift. For example, if you're trying to learn a mapping from a dashboard camera to mapping to how much you should steer the wheel, at some point maybe you're going to start making some small mistakes. And what will happen is that you're going to start getting images that are sort of significantly different from the ones that you have seen at train time. Because maybe during training time, all the images were generated by an expert, so it was driving fine, and maybe you always have the center line of the road always clearly there. But if you start making some mistakes and you start driving a little bit off the road, and you're starting to see images that you haven't seen in your training set, and the policy is going to perform worse and worse, and this will accumulate, and eventually it will fail. The other issue is that this kind of approach, this standard supervised learning approach, does not really capture the fact that these decisions, these actions that are made in these systems are actually purposeful. So they actually come out as the solution of some kind of planning problem. We're making decisions we're making these decisions because we have some goal in mind that we're trying to achieve, and so these kind of method in this kind of approach completely forgets about that. And so it might not be suitable because it completely forgets about the structure of the problem. The fact that these actions are actually coming out as the solution of some kind of optimization problem, a planning problem. They are optimal with respect to some kind of objective function. So one way to try to take the structure of the problem into account is to think about an estimation problem that looks like this. We know that there is an expert which has some policy by E, and we get to see some trajectories that are generated by the expert. And we know that there is an environment, there is an MDP, and we know that this policy is supposedly optimal with respect to some kind of cost or reward function. I guess before I was using rewards. From now on, I'm going to use cost functions, but it's the same thing. It's just you can think of the cost as the negative of the reward. So what we can try to do is we can sort of try to come up with, leverage the structure of the problem, and try to come up with a cost function that rationalizes the behavior that is demonstrated by the expert. And what I mean by that is that it should be the case that the kind of cost function that we get by solving this inverse optimization problem should be such that if we plan using that cost function, if we try to find optimal behavior with respect to this unknown cost function, we should somehow get back the behavior that we started. So the assumptions here are that the expert is following some kind of policy, and that the it's not working. Well, do it like this. Oops. And that the policy is optimal with respect to some unknown cost function. Now, one problem with this approach is that it's unfortunately ill-posed. And it's easy to see that any policy is optimal if all the costs are all zero. So if all the costs are zero, so nothing matters in the environment basically, then any policy will be optimal. And so in some sense this problem is ill-posed because whatever policy we start with here, whatever trajectories we have here, it's always possible to rationalize them with a identically zero cost function. So to solve the problem, we have to regularize in some way. And so one way to think about this problem is to try to do something like this. Intuitively, we want to learn a cost function such that if we plan with respect to that cost function, so if we try to minimize the expected cost as a function of the policy, we get back the policy, the expert policy. As we know, that one is not, this problem is not well defined, and so we're going to add some regularizer here. Now, how do we solve this inverse optimization problem? How do we come up with a cost function such that this equation holds? One way to do it is to do maximum causal entropy inverse reinforcement learning, which will basically correspond to solving the following optimization problem. So we're gonna, let me try to parse this for you. So there is a max over cost functions, and then we have two terms. So what we're trying to do here is we're gonna try to find a cost function such that this expression here is large. So what we're going to try to do is we're going to try to make this quantity here as small as possible. And notice that this quantity here is the expected cost with corresponding to the expert policy. So we're going to try to give a small cost to the expert. In order to maximize this whole expression, what you should do is you should basically try to give a small cost to the expert, and you give a high cost to everything else. The minimum over all possible policies of the expected cost has to be high. And intuitively, if we can do this, then when we solve this optimization problem, we're going to get back the expert policy. Because the expert policy is the one that has the smallest cost. Everything else has a high cost. So if we try to plan with respect to a cost function that we obtain this way, we should get back the expert policy. Does it make sense? Yeah.
Can you say again what's the intuition behind why you're sticking in the regularizer?
So think about the following case. What if the cost function is identically 0?
Right.
Then essentially any policy is optimal in that case, right? So you could always rationalize and explain any behavior that you see, any trajectory, by saying the cost function is 0, and definitely those trajectories that I saw are optimal with respect to that 0 cost function. But that's not what we want right there. And so we regularize.
Yeah, that makes sense.
Yeah.
An optimization problem consists of two very different types of information: constraints and the objective. I think we should try to be learning them by different strategies. It seems to me the constraints is something you can learn with traditional supervision type machine learning. Maybe the objective you can't. But now you're lumping them into the same pot. And at least in my mind, it's not clear that's a good idea.
So which constraints would you?
For example, that I have to stay in my lane or something like that.
I see.
I have to stay on the road. That's a constraint. And I think this I can learn.
Yes.
Just from the traditional kind of supervised learning.
Yes.
The objective of how to get to my destination is something else.
Yes.
But keeping very different things and putting them into the same pot may not give you the optimal.
That's a good point. I guess I don't know if there is much work on trying to work on constrained MDPs. Sort of like right now, the object that the planning sort of setting that we're considering is that of an MDP, where we don't have constraints, and so everything is encoded in the reward, the cost function. So the constraint that you don't want to get off the road is encoded in the reward function. So that's the only object that we can play with to represent the behavior. But it's a good point that maybe it would make sense to consider constrained MDPs and sort of try to put some of the effort in sort of trying to learn constraints, and it would make learning the reward function. So, yeah.
So having that H pi is basically a way of incentivizing certain kinds of policies more, okay?
Yes, and I haven't told you what that H pi is. It's going to be causal entropy. Basically, we're going to try to say that policies, so we're going to be thinking about stochastic policies, and we're going to say that we prefer policies that have a high entropy on which actions you're going to take in each state.
Say it again?
So you prefer a policy that has high entropy over the possible choices of actions. And this is something that can be justified in different ways. In the econometric literature, they call these things dynamic discrete choice models, and you get them by assuming that the decision maker is optimal, but with respect to a reward function that you basically you assume that there is an underlying cost function, but in some sense there is some noise that is visible to the agent, but is not measurable by the modeler. And if you assume that that noise is distributed as a Gumbel random variable, like an extreme value distribution, like the log of a uniform random variable, then it turns out that you get exactly the same thing. And you get this causal entropy. It's not going to be very important, the regularizer. But this is the basic setting. So how does this work in practice? How do you actually get an algorithm? basically the algorithm is something like this. We're going to start with a guess. How do you actually try to solve this optimization problem? What you do is you start with a guess for the cost function. You run reinforcement learning or a planning problem with respect to that cost function. You get some behavior. You compare it with the expert behavior, with the trajectories that you have from the expert. And then somehow you figure out a way to update the cost so that the behavior that you get looks similar, more similar to the one provided by the expert. And then you obtain a new cost function that is slightly better. You run RL again, and you keep doing that. So basically, there is a gradient computation here, where you're comparing your behavior with the expert behavior, and then you take a gradient step there, and then you solve a planning problem. You keep doing that until you converge. The problem of this is that it's somewhat indirect. Everything is posed over costs, not policies. It's very expensive because you have to solve a planning problem, an RL problem inside a learning loop. You have to solve many learning problems, planning problems inside. And if you cannot solve them to optimality, so if you cannot find the globally optimal policy, this is not even guaranteed to converge to anything. So it might actually diverge. So what we try to do is we try to see, well, can we actually first work directly over policies? So if at the end of the day what we want to get is a policy that looks like the expert, perhaps we can forget about this more complicated loop, that is always sort of thinking about costs, and can directly try to characterize what is the policy that we get by planning with respect to a cost function that we obtain. And by doing that, we'll be able to get rid of many of these problems and also come up with new algorithms. So the first step is to try to characterize the kind of policy that we get if we plan optimally with respect to a cost function that we obtained from inverse reinforcement learning. So there is the inverse reinforcement learning problem, which is the one I had before, which is a way of going from demonstrations to a cost function. So remember, before we were maximizing over costs of this expression, where we had one term corresponding to all possible policies, and then we had the cost of the expert policy. And now we're going to consider this more general version of IRL. We're going to call it a psi regularized IRL, where we're not just looking for, we're basically adding a penalty term here, which we'll see later becomes quite important in this case. Then remember, there is the reinforcement learning step, which is the one that gives us a policy from the cost, which is just basically finding with respect to the cost function that we obtained in the previous step. Finding the best policy that minimizes the cost that we found. So a natural question is, what are the properties of the policy that we get by combining these two operators? What do we get if we combine if we plan on the policy that we get by running inverse reinforcement learning? And we directly characterize that and then use it to come up with different or better algorithms. And it turns out that you can characterize this policy that you get by running reinforcement learning on an inverse reinforcement learning problem as effectively trying to come up with basically trying to match two objects, which are the occupancy measures. So the result is basically saying this. It's saying that the policy that you get by planning with respect to a policy with respect to a cost obtained by our IRL is just trying to match to get as close as possible to the occupancy measure that is given by the expert policy. And an occupancy measure is just a distribution of state actions that you get when you navigate the environment using a certain policy. So rho pi e is the occupancy measure of the expert, which is just the distribution of state action pairs that you see when you navigate the environment using the expert policy. And so it turns out, and rho pi is the occupancy measure that corresponds to policy pi. So it turns out that by running RL over and then combining these two operators, RL and IRL, what you're trying to do is just matching, trying to match these occupancy measures. And the distance between these two distributions is given by this psi star, which is just the convex conjugate of psi. Before I was assuming that psi is convex. So a few examples. Well, maybe the takeaway is that the typical IRL definition is that it's a procedure for finding a cost function such that the expert policy is uniquely optimal with respect to that cost function. This result will basically provide an alternative view on IRL, which is saying that IRL is a procedure that is trying to come up with a policy that induces an occupancy measure that is close to the one given by the expert. And closed is measured with respect to this psi star. And so depending on how we choose this regularizer psi, we're going to get different kinds of algorithms. Some already known, and some we're going to see are going to be new. So the simplest sort of case is to choose psi to be a constant, so don't regularize. And in that case, you can see that if we try to run RL over IRL, the result that we get, the policy that we get, is such that the two occupancy measures are going to be identical. They're going to be exactly the same. So this is, of course, not what we want. This is not a really useful algorithm, because in practice, we don't have the expert policy. In practice, we only have samples. And so what this will do is it will basically overfit. We're giving it too much flexibility in choosing the cost function and the policy. And so what it would do, if we don't regularize in any way, is it will just come up with a policy that will give you exactly, that will visit exactly the kind of state and actions that you have in your training set. So this is not really what we want. A more reasonable solution is to consider a simpler class of cost function, which you can think of as adding some kind of regularization. And in particular, we're going to think of cost functions that are linear in some previously some chosen features of the states. And if we do that, it turns out that if we choose basically a regularizer that will, in our psi regularized IRL, if we choose a regularizer that will only allow cost functions that have this form, it turns out that we get apprenticeship learning, which is another pretty popular algorithm from the mid-2000s. It turns out that what you get by that you can recover apprenticeship learning by basically doing reinforcement learning on this psi regularized inverse reinforcement learning with that particular choice of regularizer. And so apprenticeship learning is just doing something very reasonable. It's saying it's going to try to imitate expert behavior by finding a policy pi that will perform better than the expert with respect to the worst possible case cost function. So it will try to solve this optimization problem. We try to minimize the maximum difference between the cost that we incur with the policy pi and the cost incurred by the expert. So for example, if this difference is negative, then we're doing well, because it means that the cost that we incur with our policy pi is going to be smaller than the cost, even smaller than the cost given by the expert. So it turns out that this is a special case of our work, of our framework, if we choose psi in that way. Now, this tends to work reasonably well, but it requires some very careful choice of the features. And unless it is the case that the true cost function that the expert is optimizing for is really in this set C, it's really a linear combination of those features, then there is no guarantee that this approach, that apprenticeship learning, will actually recover the true expert policy. So it really has to be the case that the expert is optimizing for a cost function that is a linear combination of the features that you chose. If it's actually optimizing for a slightly different cost function, then you don't have any guarantee that you will recover anything close to that. And you can sort of see it if you think about this interpretation of as a combination of reinforcement learning and inverse reinforcement learning. In some sense, inverse reinforcement learning is encoding the expert behavior as a cost function in this set C, which is just the set of linear cost functions in the features. And then the reinforcement learning step here will try to decode the policy based on the cost function. And but if the set C of cost functions that we're thinking about, if our features are too simple, then it might not be possible to do this decoding step and go back and recover that. So finally, we get to the title of the talk, so the generative adversarial part. We saw before that one of the issues of apprenticeship learning is that the class of cost functions that we were able to consider before was too simple because it was just like linear functions in some predefined set of features. So what we would like to do is we would like to consider a more complex class of cost functions. And so this generative adversarial imitation learning is a different approach to think about the problem, is a different kind of way of measuring distances between occupancy measures that will allow us to consider much more complicated class of cost functions like say, deep neural networks. And so the idea is as follows. What we will try to do is we're gonna try to find a policy, pi, such that given the best possible, and we're gonna at the same time we're gonna try to find a discriminator, D, that will try to detect whether a pair of states and actions are generated by the expert or are going to be generated by the policy. So we're going to generate a policy. We're going to try to find a policy pi that will essentially map noise to a distribution over states and actions. And at the same time, we have a distribution over states and actions that is given by the expert. And we're going to try to essentially find the best possible discriminator that will try to distinguish between samples generated by the true samples and in some sense the fake one that are generated by our policy. And so this is closely related to generative adversarial networks. If you've seen this before, this is a very popular type of generative models, especially for images, that works in a very similar way. It's trying to build generative models of images that takes as inputs some random noise and outputs an image. And these models are trained with a very similar objective. That is, they are trained, there are two components of these models. There is a generator and a discriminator, like what we had before. The generator is trying to map random noise to images, and then the discriminator is trying to distinguish between the real samples and the fake ones. So it's trying to sort of output high values, in this case for the real samples, and it's trying to output low values for the fake ones. So in some sense, you can think of this as a game where there are two players. There is a generator that is trying to generate images that are as realistic as possible. And then there is a discriminator that is trying to distinguish between the fake images and the true ones. And you're jointly training these two so that they are competing. So the discriminator is trying to do as good as a job as possible as distinguishing these two samples. And the generator is actually trying to fool the discriminator. And in some sense, you can see that this is doing the right thing, because in order to fool the discriminator, the generator has to produce images that look like the real ones. So if they don't look like the real ones, then the discriminator will be able to sort of pick out the differences and will get an advantage in the game. And so in our case, we're doing the same thing, except that we're not dealing with images, but we're dealing with the distribution of states and actions in an MDP. But it's a very similar idea. We have a game between two competing agents. There is the policy that we're trying to find, and there is the discriminator which is trying to distinguish between the true samples and the ones that are coming from the policy. And it turns out that this comes out as a special case of our previous formulation. It turns out that there is a choice for that psi such that the way to measure the distance between the two occupancy measures, the one corresponding to the expert and the one given by the policy, is given by, when you think about when we use this expression, it turns out that this is equal to the Jensen-Shannon divergence between these two occupancy measures. And so that's sort of like another way to think about this algorithm, is that we're basically trying to come up with a policy phi that minimizes the distance between these two distributions as measured by this Jensen-Shannon divergence. Then, of course, in practice, we cannot really optimize over all possible discriminators. So what we're going to do instead is we're going to pick a sufficiently complex class of discriminators, like a neural network, and we're going to try to jointly optimize over policies and the discriminator. So how do we actually optimize it? How am I doing on time? Okay. Almost done. So previous approaches to apprenticeship learning usually required access to a model of the dynamics of the MDP, and they could only work on small environments because they required solving this RL problem with another loop. So instead here, what we're going to do is we're basically just going to do gradient descent over a restricted but sufficiently complex class of policies, and at the same time the discriminator. The advantages of doing policy gradients is that we're guaranteed to, under some conditions, to at least converge to a local minimum, and we can do it in a model-free way. The negative sides, of course, of policy gradients is that the gradient estimates can have very high variance, so we might need to take very small steps if we want to converge reliably. So we solve these issues using TRPO, which is basically just a way to sort of take small steps, relatively small steps, to guarantee that sort of the distributions over states and actions don't change too much. It turns out that this approach works quite well. So here is one example on this highway driving task. This is one of the policy that we learned doing imitation. So here we are going to try to learn how to drive this blue car, and the inputs to the policy are the observations that you get from these egocentric sensor. It's basically giving you the distance to the points on this LiDAR-like sort of sensor. And so we provide different types of driving behaviors, more aggressive, like a tailgater, and a more defensive kind of driving. And then we try to use this approach, sort of trying to come up with a policy such that a discriminator cannot tell apart the occupancy measures of our policy and the one given by the expert. And as you can see, it turns out that it's doing a pretty good job at this task. You can also do, we also tried it on this task from the OpenAI gym, Joko environment. Here we are trying to learn how to control this, the humanoid robot and this ant kind of like robot. And again, what we did is we provide demonstrations. We provide some demonstrations on how to control all the joints so that the human, this robot is sort of like doing the right thing. And then we try to see whether we can imitate the behavior by finding a policy that's sort of trying to solve that objective function. More. Oh, question, yeah.
Generally, how many demonstrations do you need?
Yeah, good question. So I have it here. So here, I'm showing some plots showing as a function of the number of trajectories in the expert, how well it does compared to the expert. So the expert is the dotted darker blue line here, 0 normalized to 1. So you can see that in some cases, like the humanoid, you need maybe a few hundred. In some cases, like the ant, you don't need too many. I think they're pretty close, maybe 20 or so.
So what is the expert here? I mean,
Good
for
question.
restrictions, it's not obvious how to make them move, right?
Good question. So the car was actually
The car is fine.
driven by the grad student. In this case, but we actually solved the RL with a given reward function, and then we generated the sort of trajectories with respect to the policy that we got from RL, and then we tried to see whether we can. So we can see that it does fairly well. So here we compared with basically behavioral cloning is the approach that I showed at the beginning, where you're just trying to do supervised learning, you're just trying to map states to actions. You can see that in some cases it does fairly well, like in the ant case, but in some cases it doesn't do very well. Walk or relatively low compared to what we can do with this generative adversarial imitation learning approach. And then we also compared to the other lines correspond to what you get. Well, there is a random, which is of course really bad. And then we compare to GTAL and FEM are basically what you get if you consider much simpler cost functions that are just linear in some set of features. And so this is kind of showing what you gain by using a more complex class of cost functions in some sense. You can think of the discriminator that is trying to distinguish between states and actions generated by the model versus the true ones, as essentially giving you a more complex and more powerful class of cost functions that can be used to discriminate between different types of behaviors. Yeah.
Sorry, it seems for the humanoid and for the half cheetah, your method sometimes dips over what the expert can do. Like it outdoes the expert. What's the explanation for that?
That it does better?
Yeah.
It's possible because we got it from we got
You're
it
just
from
building
around.
on what you already had.
Yeah, like that's something that you can get even if you think about the objective that you have in an apprenticeship learning. What you're saying is that you're trying to find a policy that does better than the expert with respect to the worst possible chosen sort of cost function. So it is possible. You're not just trying to match the expert, but you're sort of trying to make the margin as big as possible. Yeah.
So your performance metric is something that's totally external in all of these experiments, like the your none of these policy constructors know your actual performance metric, or do they?
We don't have access to the reward.
Or, no, I know, but when you're plotting the the scale performance, this is some external thing that's completely unknown.
This is the actual reward.
Right.
That we trained the system on.
Yeah. Okay.
Because we started with some reward, and then we did RL on that. So, yeah.
Did you compare with Dagger, another forms of imitation?
Dagger?
Yeah.
So that one requires some kind of help from the human, right?
But don't you start with expert trajectories?
But these ones are kind of generated from RL in this case. I guess you could maybe do it. We didn't compare with Dagger. I wonder if it may be possible.
Because isn't the same interface you get an expert trajectory and you're trying to derive a policy that's somehow like this.
Right.
You could use Dagger.
It's kind of like behavioral cloning,
Yeah.
but it's sort of saying that whenever you make a mistake, you're sort of the human or the expert will tell you what mistakes you made and you can try to correct, right? That, if I remember correctly.
Yeah, that's how.
Yes.
So I mean, yeah. So it's better than behavioral cloning.
Yes.
Because it resolves cascading errors a little bit.
Right.
So.
We haven't compared with that.
We have 3 more minutes.
Cool. Yeah. So just what we're trying to do next is we're trying to do it on torques. These are some videos. This is just trying to. This is not imitation. We're just trying to learn a policy. This is actually like an open source simulator. So what we're trying to do is we're not trying to see whether this can be extended to more complicated inputs. Before we were basically assuming that, say, in the highway driving case, we had access to this sensor, this egocentric sensor that was giving us distances from all points. Now we want to do it from, say, raw images. So we are playing with this simulator. This is what you get. So this is what you get if you actually use affordances to drive the car. If you try to do it on images, it's a lot worse. It's something like this. This is ongoing work, but this is pretty bad. It's very, very choppy kind of thing. And yeah, so that's the next thing, is trying to see what we can do with whether we can actually do imitation in this with these more complex inputs. That's it.
We have 1 minute for one question.
Yeah.
Did you initialize with behavioral cloning, or did you learn it from scratch?
It's initialized with behavioral.
Okay.
All right. Thank you.